My name is Elliot Slaughter, and today I'm going to talk about TaskBench, a parameterized benchmark for evaluating parallel runtime performance. This is joint work with collaborators at Slack, Los Alamos, Purdue, Stanford, University of Tennessee, Knoxville, and NVIDIA. As a user or developer of parallel and distributed programming systems, one of the things that you commonly want to do is benchmark performance. But benchmarks and proxy apps are expensive to implement. And in general, if you have n benchmarks in m different programming systems, then the total effort required to develop, test, debug, and tune the code for performance is the product of n and m. So you can see this visually. If you have n benchmarks in m systems, you have to implement all benchmarks for all systems. And what happens is that in practice, not all of those implementations arrive at the finish line. So maybe there's not enough time, maybe there's not enough money, there may be bugs, some may be incomplete, or maybe they're just not fully tuned. And as a result, you can't actually use them in a comparative study. And so the result is that few papers actually evaluate large numbers of systems. In TaskBench, we aim to reduce this effort to the sum of n and m. And the way that we do that is we introduce a new core API, the benchmarks are implemented in terms of this API, and then the systems implement this API. And the result is that each system automatically implements each benchmark. Now, the way that we do this is we explicitly model the space of application behaviors. And the insight that we had is that it's possible to model the application as a task graph. A task graph is a directed acyclic graph where the nodes are tasks and the edges are dependencies. And note that in our view, we're using task in the broadest sense of that word. So a task is just any unit of code that does not contain communication. And therefore, it makes sense to talk about tasks even in models that do not have a native notion of task. And we can model different applications by parameterizing the task graph along a number of different dimensions. So for example, the iteration space, the set of tasks to be executed, the dependencies between tasks, the kernel executed by each task, and the data produced by each task, and therefore communicated by dependencies. And each of these dimensions gives us a way to model applications with different behaviors. Now let's look at some of the specific dimensions of that search space. A task graph in our model is the product between an iteration space and a dependence relation. In our model, an iteration space can be seen as just a set of tasks. So this could be a grid, for example. And we view time as flowing from top to bottom, so dependencies point backwards in time. And along the horizontal dimension, we have parallelism. So these are tasks that could plausibly execute in parallel. The dependence relation determines which tasks depend on which other tasks. And we can use this to specify a bunch of different structures of the task graph. Both of these can be arbitrary, and that means that we can specify a number of different patterns using this technique. So for example, we can make a stencil pattern by connecting each task to its two immediate neighbors. We could do FFTs with butterfly exchange. We could do random task graphs. We could do sweeps for the discrete ordinance method. Or we could do trees for divide and conquer algorithms. And so we can simulate a number of different application patterns using this technique. And this is also an extensible set. So if you wanted to add new things over time, you can do this. And any patterns that you add are immediately available to all of the systems that implement TaskBench. Every task in the task graph executes a kernel, and we provide a number of kernels that are built into TaskBench, including empty kernels to measure overhead, as well as compute-bound kernels, memory-bound, kernels that randomly vary in duration to simulate load imbalance, and again, this is also an extensible set, so new kernels can be added over time. And because they're implemented once for all of the systems, that makes it possible to do apples-to-apples comparisons between systems because we know that we're running exactly the same code. We implemented TaskBench in 15 different parallel and distributed programming systems, including traditional message passing models for HPC, MPI and MPI plus X with OpenMP and CUDA, PGAS and actor models, Chapel, Charm++, and X10, a number of task-based models, including OMPSS, OpenMP version 4 with task dependencies, Parsec, Realm, Regent, and StarPew, and a number of models for data analytics, machine learning, and workflows, including Dask, Spark, SwiftT, and TensorFlow. And so we've covered a number of models used in HPC as well as some used more commonly outside of HPC. And in all cases, we contacted the developers and we thanked them for their help in making sure that we're able to provide the most highly tuned implementations for each of our implementations. TaskBench makes it possible to gather a large amount of data, and therefore we need a way to quickly compare performance in all of these different configurations. We need a metric that's going to enable us to do that, and we'd like it to satisfy a couple of goals. One is that we'd like to constrain efficiency. We'd like to know how much useful work has been performed. And the reason is, if we choose large tasks, those could hide any amount of overhead. And if we choose small tasks, then we may not be accurately representing the performance of the system. We also want this metric to produce a single number, and that makes it possible to plot it against a number of different axes. So for example, we can plot against node count to do a scalability analysis. And so we developed a new metric, METG, the minimum effective task granularity. METG of a given efficiency threshold, say 50%, is the task granularity such an application achieves an overall efficiency that is at least that threshold. This is a parameterized metric, and that means that you can choose an efficiency metric that best matches your application. If your application is most readily analyzed in terms of, say, peak performance, then you can compare against the peak performance of the machine. If you have a machine with, say, 1.2 teraflops of peak performance, 50% of that is 0.6, and then the METG of 50% is the task granularity such that the application achieves 0.6 teraflops. Or if you have an application that is not readily analyzed in terms of peak performance, that's fine. You can also use an application-specific metric. So for example, if you're doing some sort of a simulation on a mesh, you could pick mesh cells processed per second as the metric. If your application in its best configuration hits 1 times 10 to the 9 mesh cells per second, for example, then 50% of that would be 0.5 times 10 to the 9. And the METG of 50% would be the task granularity that hits that rate. Again, this is an efficiency constrained metric, which means by definition useful work is being performed. And it also exposes overhead. Because we're looking at the minimum effective task granularity, we naturally find the limit of the system under load. Now we're going to measure METG as a two-step process. In the first step, we're going to measure performance with decreasing problem size. So the way to read this graph is from left to right. We start on the far left with a very large problem size, and then we gradually decrease that problem size until performance drops. In this case, we're using a compute-bound configuration of TaskBench, where we simulate problem size by controlling the number of iterations that the compute-bound kernel runs for. In the second step, we convert this to an efficiency versus task granularity plot. With efficiency on the y-axis, this is just the percentage of the peak flops achieved, and task granularity on x-axis. That's the total running time divided by the number of tasks. And the way we calculate METG is by taking the intersection with the threshold efficiency curve. In this case, that's 4.6 microseconds, and that gives us the METG 50% for this application. One of the things to keep in mind about METG is that it is a minimum effective task granularity. So as an example, if you had two systems with METG values of 1 millisecond and 10 milliseconds, and if you look at an application with an average task granularity of, say, 100 milliseconds, then the difference between these two systems is not going to be that large in terms of performance, because the task granularity we're looking at here is much larger than the overhead of the system. As we continue to drop that, if we go to, say, 10 milliseconds, we're going to start to see some divergence. And as we continue going, we're going to see a much larger difference because we've now dropped below the overhead of one of the systems. And so essentially what METG does is it imposes a floor on the task granularity that can be considered to be efficient. But if you're running an application with larger task granularities, this might not actually make a difference to you. While we were developing TaskBench, we looked at a number of other performance metrics, but ultimately decided that they were not the right choice for our experiments. Strong and weak scaling are generally the right choice for application performance, but they don't generalize. If you pick a large problem size, you might hide overhead, and if you pick a small problem size, that might not accurately reflect the actual performance of the application. And in general, it's impossible to predict from a single set of strong or weak scaling runs how the application is going to perform at any other problem size. Tasks per second is a second metric and has much the same issue. Large tasks hide overhead, small tasks may not reflect performance accurately. METG avoids both of these issues by using a fixed efficiency threshold. And in fact, we can also use METG to predict other metrics. For example, the paper shows that we can predict strong scaling to within a bound using our METG measurements. We evaluated all 15 implementations of TaskBench on up to 256 Haswell nodes of the Cori supercomputer. And since TaskBench can cover such a broad space of applications, we basically asked how many different experiments can we run with this tool. We ran compute-bound experiments, memory-bound, scalability experiments with different dependence patterns, numbers of dependencies per task, communication and computation overlap, load imbalance, and GPU experiments. All of these are included in the paper. I will not have time for them in this talk. I will only cover a subset, but please see the paper for details. We performed a number of scalability experiments by measuring METG at different node counts for each of the systems. And one of the things to notice about this graph is that the results span 5 orders of magnitude. So clearly there is a huge amount of variation in the basic overheads of these systems. In general, we observed that the systems tended to fall into certain buckets. So the systems for data analytics, machine learning, and workflows tended to be among the ones that had higher overhead. Task-based systems for HPC tended to be more in the middle, and the most efficient systems tended to be those that were explicitly parallel, so message passing, actor models, and PGAS, for example. As we measure more complicated dependencies, one of the things that we notice is that the graph tends to become more compact. The gap shrinks between some of the systems. The systems that are explicitly parallel and asynchronous tend to gain an advantage here, and the systems that are task-based, that were more in the middle before, are approaching the systems that are explicitly parallel. And so these more complicated dependence patterns seem to favor systems with asynchrony or other complicated mechanisms, and seems to make the efficient mechanisms of some of the lowest overhead systems less relevant in these configurations. One of the things that we can do with this data is to look for trends. And for example, we found that when we looked at the task-based systems, there was a gap in the scaling between the implicit and the explicit versions of these programming models. This gap exists because in the implicit versions, a single node is responsible for analyzing all of the tasks that execute on the system. And this is not fully mitigated by the approaches that have been adopted by these systems. On the other hand, compile time techniques, like used in Regent, do have the ability to mitigate this bottleneck, and we found that Regent, with an implicitly parallel programming model, was still able to achieve good scalability. We also looked at the overlap between communication and computation. So in this graph, on the left side, we have the compute-bound case. On the right side, we have the communication-bound case. And in the middle, we have balanced communication and computation. And we found that systems with an asynchronous execution mechanism were able to gain an advantage as long as their overheads weren't too high. So any system with METG 50% of lower than approximately 100 microseconds was able to demonstrate an advantage, but systems with higher overheads struggled to demonstrate that. TaskBench has a number of limitations that are important to keep in mind. One is that we don't measure productivity. We only look at performance. As you saw, there is a large gap in the overheads between the most efficient and least efficient systems we looked at. And yet, there are popular systems at both ends of that spectrum. Clearly, the higher overhead systems provide benefits which make them worthwhile to use. We also don't look at how the kernels are written. We intentionally standardize them in order to make the comparisons fair. But this is actually a case which in real applications might make a substantial difference. We don't look at sparse data. All of the task outputs in TaskBench are dense. And though we provide GPU results, they're currently limited, and we only look at MPI plus CUDA. In the future, we would like to look at how to model specific real-world applications with TaskBench, asking the question what TaskBench configuration most accurately models the behavior of a given real-world application. In conclusion, even the best systems achieved an METG 50% of about 100 microseconds when we scaled past 100 nodes. And as a result, the efficiency of, for example, MPI seems to be less relevant at larger node counts and as the dependencies become more complicated. Asynchronous systems achieved better overlap between computation and communication, as well as better support for complex task graphs. But this was dependent on their baseline overheads not being too high. So as long as the METG 50% was less than about 100 microseconds. Task-based systems show a scaling bottleneck which does not seem to be entirely resolved by existing approaches to task pruning. On the other hand, Regent's compile time approach was able to resolve this bottleneck while preserving the original implicitly parallel programming model. High overhead systems such as Spark are obviously popular, and so clearly these systems provide other compelling benefits that are not measured by TaskBench. We are very grateful to have received support from a number of sources, including the Exascale Computing Project, and with that, we're happy to take any questions. Thank you.